Okay, so let's get started first with one illustration of the positivity invariance issue, the one with, let's say, the harvesting model. So let's use the D-field plotter. Let's see, the equation that we wrote was R times P minus H. So notice that in p-plane you can actually introduce parameters here, which is in this case R and H, the harvesting rate. And let's make the time positive, and you may have to play around maybe a little bit with the range for P. Normally we put the positive range for the population because the models we work with are valid. In other words, they follow the positivity condition or the positivity invariance. But this time, because this one will drop into the negative part, I'm gonna choose a range which is also negative for P. So let's say R is equal to 1 and H is equal to 2, so the equilibrium is 2. Or even, let's actually make 20 so we can see it better. So if you run the phase plane, and let's see, where is that direction field? Yeah, notice that the equilibrium at 20 is over here. So if we start with P above it, then obviously the solution goes to infinity exponentially. If we start below it, it goes not to 0 as you may think, but to minus infinity. So that is the problem. I mean, normally, if you, for example, if I want to use the model for the time range beyond 2, then it's going to be invalid, right? So it's only as good as running the model between 0 and 2. Because after that, the solution doesn't make any sense, right? If you start with a population below 20, then it goes to minus infinity. Again, in truth, the harvesting model is used just to kind of get an idea basically on how much harvesting you should do in comparison with the current population, so that you can avoid the population decline. So with the present level of harvesting, then if you are above 20, then you should be fine. So it's not completely useless, but it's technically an invalid model because it predicts negative population if you start with a positive condition. When I said bounded away from 0, remember my example in the previous part. I had an equation x prime equals 5 minus x. So not only the solution stays positive if you start above 0, if you notice here actually it's bounded away from 0, so it doesn't even come close to 0. And that's the effect of what I said in the previous part, that if x is close to 0, x prime is strictly positive. So if x prime is strictly positive, if x goes to 0, actually it means it will never go to 0. So not only stays positive, but it stays bounded away from 0. So having said that, let's actually move on with some examples related to the epidemic model, SIR model. Now notice that, so for that we're going to use p-plane because we have to introduce two equations. In the SIR model, it's true we have three equations and p-plane only allows us to run two equations, but as it happens, the first two equations depend only on S and I. So we can treat the first two equations as a system of two equations and two unknowns. I'm going to choose, there's no way to write Greek letters here, so I use big L for lambda as a parameter and R the recovery rate over here. So assuming we're going to have 100 initial, let's write it here, it's not part of the model, but let's say S naught, as I said in the previous part, the number of susceptible is 100, and the number of infected is 2 people, the I naught. So the total population is 102. You don't have to introduce these values because they are not part of the system, but I just want to have them here to emphasize. Because when you run the model, you have to be careful to enter valid input. So if you make up your mind that your population is 102, you can't enter as an initial condition anything above 102. The math won't get upset, right? Because the model will run anyway, but under your assumptions in the model, you're stuck to enter initial values that are below 102 if that's your total population. And notice that if you look at the epidemic reproductive number, let's see, he doesn't like, I'm gonna call it That's kind of an unfortunate thing, because R naught is the let's see, how do I do that? The reproductive number. Let's call it REP. Because R naught is R of 0, but typically R naught is the notation for the reproductive number. So we could do this. I mean, I chose the 100 values for S naught to make it easy to estimate the size. So notice that if I multiply lambda 0.02 with 100, because the reproductive number is lambda S naught times over R. So if I multiply by 100, that's going to be 2. 2 over 0.5, that's going to be greater than 1. Right? So that's going to be greater than 1 in this example. If I run the model, so notice that if you pick a valid initial point, so 102, right? It means, so let's roughly speaking, if I choose S to be 100, so S is on the horizontal line, I is the vertical line. So let's say 102, 100 for S and 2 for I, somewhere here. When I click on it, notice that I goes up first and then declines to 0. Okay, so once again, the I values are on the vertical axis. So growth, peak of the epidemic, and then decline to 0. Let's say I start with 50 susceptibles and 52 infected. So somewhere here, I guess, approximately, right? By the way, the solution is plotted in backward time as well. Let's actually change that and choose the solution to be plotted just in forward time. And so then 50, 52, somewhere here. So again, lots of people become infected, right? Because the final size, I mean, notice you start here and then the final size of S is very small. It's not 0, but it's very small. I always goes to 0. If I start somewhere here, notice that I start basically with very few susceptibles, right? So then the epidemic is a little bit less pronounced. You're going to have a smaller peak, or not much of a peak at all, right? If S naught is very small. So if S naught is small, you don't have any peak, because the reproductive number depends on S naught. You need a big S naught enough so you could have a peak to begin with. So no peak here, bigger S naught, you always have a peak. On the other hand, if the recovery rate is big enough, you won't have any peak whatsoever, because R naught is less than 0. So let's say R is going to be 3. So notice that in this case, 0.02 times 100, that's 2. So under my constraints that the population is 102, no matter where I start, there's not going to be any peak. Notice that the population of I of t goes to 0 without any bump. So there's no increase first and then everything goes to 0. The question still remains, for a given initial condition and a given set of parameters, what's the final size? So I mean, what are these numbers where the population stops for S? We know that all of them stop at I equal to 0. We don't need anything extra to understand that. Let me get rid of this. But the question is, what's the final size of S? Because the final size of S will tell me how many people were infected to begin with. So we could do this. Let me show you this with Wolfram Alpha. We don't need to do this with Maple yet. It's all overkill. Just to solve a simple equation, we could do it with Wolfram Alpha. So I already entered the equation Wolfram Alpha. You may want to help Wolfram Alpha a little bit by specifying that you're looking for a variable which is positive. And just enter solve and the equation. So let's see, I want to run the examples I did in the previous part. So we're going to keep lambda 0.02 and let's play with the recovery. So small recovery first, 0.5. Run the equation and then notice you're going to have two values. That's why it's what I said, it's very important to not forget the big picture and the constraint in your model. So the constraints in your model is that your population is constant, 102. So Basically, even though the equation may have other solutions, the only valid ones are the ones below 102. So the final size of S is 1.8, which is approximately 2 individuals. Lots of infections means the remaining 98 were infected, right? If the final size of S is 2. Let's increase the recovery rate a little bit, so 1.0. Hit enter. Now we have 19 susceptible left, which means 81 were infected. And if you have a lot of recovery, let's say 3, that's a huge recovery in comparison to the infection rate. Obviously not much of an epidemic. You have 96 susceptible left, 4 were infected. So obviously it's the relative size between the recovery and the infection, because of course now if I make the infection rate to be big, then again you're going to have more epidemic, right? You're going to have, see, you go back to lots of people infected. So that's it for this week, and I'll see you next time.